Welcome back, guys, to another session. Remember on our last video on Laplace transform, or let's say our previous session on Laplace transform, we treated our first standard solution to Laplace expression. So, if you can remember, we treated Laplace of A is equal to A over S, right? Laplace will be constant is equal to what? A over S. A, which is a constant, and I gave an example and I said Laplace of 4 is equal to what? 4 over S. So this is one of the standard expression or the standard solution to Laplace of a constant we took on our last session. So let's call it 1. So today we are going to be taking another standard expression to Laplace solution. So we're going to be taking the Laplace of the exponential of at. So we're taking the Laplace of the exponential of at. Laplace of exponential at. So now we don't know the answer to this, so we're going to basically be applying the same method we used to derive the standard solution for the Laplace of a. That's what we're going to be using to derive the standard solution for the Laplace of the exponential of at. So now, if you can remember that I gave the Laplace of a function of t to be given as Laplace of a function of t is given as the integral starting from 0 to infinity, right? So the integral starting from 0 to infinity of the function of t exponential minus st dt, right? So we're going to be applying the same method in deriving the Laplace of the exponential of at. So this is another standard solution to Laplace. So I want you to be jotting down this. This is the first one, and now this is the second one. So the Laplace of the function of t, you're writing this to be, so it will be Laplace of the exponential of at equals the integral starting from 0 to infinity, right? Now the function of t given here is the exponential of at, right? So the exponential of at, right? Exponential minus st dt. Sorry, let me write it in black pen. So this is basically the exponential of at exponential minus st t, right? I replaced the function of t for the exponential of at. Remember, we're looking for the Laplace of the exponential of at. So now we saw. So basically, we're going to be applying our same method of integration before we apply our limiting values. So we're going to be integrating these factors. So now, since this is the exponential of at and this is the exponential of minus st, so basically they are both exponentials. So basically, following the rules of indices, we can say that this is the integral of this is exponential at times exponential minus st is equal to the exponential of at plus minus st dt. This is the rule of indices, which says that the exponential of n times the exponential of m is basically the exponential of n plus m. So the exponential of n times the exponential of m is basically the exponential of n plus m. So the exponential of at, remember this is the multiplication sign here, times the exponential of minus st is basically the exponential of at plus minus st. So given this, we can write this as the integral of the exponential of at minus st dt, right? So integrating this factor, before we integrate it, now let's simplify it in a more simpler term. So I can rearrange the s to the other side and put a to the other side. So I can have the integral of minus st plus at dt, right? Now I can write this to be in the form of integral of minus s minus a t dt exponential of, I brought out the minus sign, so what is left with it? S minus a t dt. So we're going to integrate this in a more easier term. So integrating this, we have, so integrating the exponential of minus open bracket s minus a t dt, right? So we'll be having, so integrating this, we have exponential minus open bracket s minus a t divided by minus s minus a, right? Because this is basically know how to integrate the exponential of the exponential, because this both of these are basically constants, right? So integrating the exponential of this is basically taking this constant to the bottom of that. So I don't need to be explaining how to integrate this. So then applying my limiting values, which from 0 to infinity, right? So I'm going to be applying my limiting value. So we have in limit of t to infinity, right, of exponential of minus s minus a divided of at divided by minus sa, right, minus limit of when t tends to 0, right, is the exponential of minus s minus at divided by minus sa. Now basically I'm applying my limiting values, because initially the integral said it's from 0 to infinity. So I'm applying my limiting values. This is to infinity and this is 0. So when limiting t to infinity, this is exponential of infinity. So exponential of infinity is basically 0, right? The exponential of infinity is basically 0, right? So we have 0 minus limiting t to 0. So this is exponential of 0, right? So exponential of 0 times s minus a is basically 0. The exponential of 0 is 1. So we have minus exponential of 0 divided by minus s minus a, right? So this gives me the Laplace of the exponential of at is equal to, now 0 minus, now minus and minus is plus, right? And 0 plus this is basically this. So this is 0 plus exponential of 0 is what, 1, right? So this is 1 divided by s minus a, right? So the Laplace of the exponential of at is basically 0 plus this is this, right? So this is 1 divided by s minus a. So basically the Laplace of the exponential of at is equal to 1 minus s minus a. S is a variable, a is a constant. S does not take a value, but a takes a value. A can be any constant, can be 3 or 4 or 1, it can be any constant. So the Laplace of the exponential of at is equals to 1 minus s. Is 1 divided by s minus a. So this is another standard solution to Laplace. So this is another standard solution to the Laplace of the exponential of at. A, where a is a constant, where a is a constant. So I want you to jot this down. This is the second standard solution to our Laplace expression. So we're going to take in an example to see how we can apply this in solving any example given on the exponential of any constant times t. So now let's take an example. Basically guys, these are the two standard solutions to Laplace questions we have successfully derived. So we have successfully derived the Laplace of a is equal to a over s, and successfully derived that the Laplace of the exponential of at is equal to 1 minus s, 1 divided by s minus a. So now, like I said, let's take an example on the second expression we derived. So for example, we're given find the Laplace of exponential 3t. So we're given to find the Laplace of the exponential 3t. So we're going to be applying this. So yeah, since we have that the Laplace of the exponential of at is equals to 1 minus s, 1 divided by s minus a. So the Laplace of exponential 3t will be equal to 1 divided by s minus. Now where a here is the 3, right? Where a is what, 3, right? Where a is equal to 3. So this is Laplace of 1, Laplace of equals to, so Laplace of exponential 3t is equals to 1 minus 1 divided by s minus 3. So now let's take one more example. This is example 1, example 2. Find the Laplace of exponential minus 5t. Now we have to find the Laplace of the exponential minus 5t. Now remember we said Laplace of exponential at is equals to 1 minus s, 1 divided by s minus a. Now in this case, a is what? comparing this to this, this is standard expression, right? So comparing this to this, we see that a is what 5, a is what minus 5, right? So the solution will be equal to 1 divided by s minus a is what minus 5, right? Minus 5. So minus minus is plus, so this is equals to 1 divided by s plus 5. So this is so far we have gone in the introduction to Laplace. So we basically, I believe you can basically get the Laplace of a and the Laplace of exponential at. So I'm going to drop a few exercises for you to tackle. So I want you to do this exercise. So exercise. Now I have one exercise for the first expression we derived and another for the second expression we derived. So I want you to find the Laplace of 10, and the second question says find the Laplace of exponential minus 60. So I believe you can tackle these two examples. So I'll see you guys on the next session on Laplace transform.